Audio Jungle. Audio Jungle.
All right. So basically, if you say shock wave. So two types of shock wave we have. Okay, two types of the shock wave we have, and both are very important. One is normal shock. Okay, another is oblique shock. So we'll discuss the normal shock first. But before going the mathematical expression and all, we'll see what is the shock actually. So the shock is what basically the it's a very thin layer, okay, when it is formed when the flow is what supersonic, okay, when it will be formed when the flow is supersonic. So first of all, the shock, normal shock or oblique shock, why it will be formed? It will be formed when there is the supersonic flow. First condition to get shock in the flow field, it is because of the supersonic flow. That means m is greater than 1. And one more very special thing, if the flow is supersonic and directly will not get shock, okay, to recognize the shock in a flow field, to recognize the shock in a flow field, you must place one object in a flow field, okay, one obstacle will be there in a flow field, and then that shock will be observed. Doesn't matter it is normal or oblique, that is the secondary part. First in a flow field when the shock will be observed, okay. So that observation is very important here. For like observation of the shock in a flow field, we need to place one object or obstacle in a flow field, then only we can observe the shock. That is the one very important point here, okay. And the shock wave are characterized by a high positive pressure, okay, variation, okay. It means that pressure variation across the shock will be very huge, okay. And a shock wave is a like one reason, okay. It is a very thin reason, and approximate the order of that thin reason is what, like 10 to power minus 5 centimeter, which is very you know which is very less actually. So here the flow is supersonic flow, means m is greater than 1, and as I told you, uh, there is the drastic pressure variation across the shock. So why this drastic variation? Actually, this formation of the shock is the uh, irreversibility, okay. It is the irreversible phenomena, okay. It's a irreversible phenomena. For that reason we cannot uh, we cannot apply any isentropic relation across the shock. So let me write the points, okay. So it's a irreversible phenomenon. It's a irreversible phenomenon. Number two, if it is irreversible, so it means isentropic relations will not work across the shock, okay. All right. isentropic relation will not work across the shock, and the very thin region, okay, order of 10 to power minus centimeter, 10 to power minus 5 centimeter, okay, across shock, pressure, temperature, density, okay, and Mach number change drastically. These are the points, okay. This is the points about the shock, okay. Always remember this is the irreversible phenomenon, okay. Fine. Now, so first we'll talk about the normal shock, okay. So for the normal shock, if you see, there is the flow field here. This is the flow field. Check. This is the flow field, and this flow field is the supersonic flow field, okay. This is the supersonic. Let's try to relate. It's very simple. So supersonic. Now this flow is what going like this, and again here the supersonic, hence the Mach number will be greater than 1. Somewhere here one object is what placed. One object is what placed. Okay. One object is what placed. Normal to the flow field. One object is what placed normal to the flow field. Then what will happen? So what will happen here? Check, it's a very simple analysis. The particles, because it's a supersonic, so whatever the disturbance, okay, whatever the disturbance, that disturbance will be behind the you can say it, because m greater than 1 means what is the m is nothing but v by a, and if it is greater than 1 means v greater than a. A is speed of sound, and this is the speed of object, you can say, okay. And speed of object, or here in the sense you can say that not object, in this case here you can say speed of the flow field, okay. It's a speed of flow field. Now check. So here speed of flow field is what greater than speed of sound. What is the speed of sound? Speed of sound is the disturbance, okay. When I explained speed of sound, that time I told this is the wave propagation, and it is actually the disturbance. Suppose there is one cracker, and if you cracker is what busted, then what will happen? That disturbance will be created, and that because of that disturbance, that wave will propagate in forward direction, and that is the pressure process, and it will reach to your ear, and then you will hear the voice. Okay, somewhere there is the cracker, okay, fine. So speed of sound, this is the disturbance basically. But if it is supersonic, then speed of flow field is greater than speed of sound. Means here in this case, speed of air is greater than speed of sound. So that disturbance first will go and it will hit to the object. Okay. So generally, if it will go and hit to the object, if it is subsonic, so subsonic means that the speed of sound is greater than speed of flow field, means m is less than 1. So if the speed of sound is greater than local velocity, then automatically speed of sound will go first, and it will hit to the object, and it will return and it will tell to the flow field, okay, something is there in front of that. You got my point or not? Otherwise, I will take two reason. I will take two reason here. Wait, two reason I will take. So then only it will be clear. Fine. So let me divide in two parts. One is subsonic, another is supersonic. So it will be more clear to you. Let me remove this part also. Now fine. Now you will understand easily. So I'm going to take this as two reason. Sorry. Two reason I have taken here. This is the two reason. This is the, you can say, uh, uh, subsonic. Okay, and this is the supersonic. All right. Now see. So it is subsonic. So obviously m will be less than 1. Okay. Now we'll start. M will be less than 1 because it is subsonic, and it is m is equal to b by a because it's a supersonic, so greater than 1. Huh? And here b greater than a. Here it's subsonic, so v less than a. All right. Now, as I told, object I will write. So I need to draw the object also here. So somewhere I will make this is the object. It is placed normal to the flow field, and here also the object is what placed normal to the flow field. So what my point is, just listen carefully, you will understand. It's very simple only. This is what subsonic. Okay. So in case of subsonic, check a, which is the speed of sound, which is also the wave propagation. Wave propagation, sometimes called disturbance also. Okay. So if a is greater than v, means speed of sound is greater than the speed of flow field. So this speed of sound is also called wave propagation or it's a disturbance. So something is what there in a flow field. So the flow field velocity is what v, check, and this velocity v is what less than speed of sound. So speed of sound will move. You can say speed of sound will move with higher speed compared to the flow field. If the speed of sound is what is higher speed compared to flow field, so it will go ahead to the flow field, and if the speed of sound will go ahead to the speed of flow field, then speed of sound will go first and hit to the this object. Okay, this object, and automatically it will tell, because behind the speed of sound is speed of flow field, it will tell to the speed of flow field that something is there in a flow field. So this flow field of flow field will try to change the direction. It will try to change the direction. So what will happen? It will change the direction. So this middle one will come and go hit here, and this rest it will go and it will turn the direction. It will turn the direction, means like this. They will turn the direction like this. Okay, like how it is possible? Simple. How it is possible? Because speed of sound is what higher here in this case, and speed of sound is higher, hence the disturbance first reach to the object, and it will recognize object is in a flow field, so immediately it will transfer the message to the flow field which is behind the speed of sound, and the message will be what, something is in flow field, so this flow field will try to change the direction. In this way you can understand, so it will change the direction. Remember, this is the first case. What is the second case? In this case, see, speed of sound is what, less than speed of the flow field, means speed of flow field is what, higher. It means first this speed of flow field will go and hit here, hit on the object, it will go and hit to the object, because it here there is no message passed, there is no message passed, okay, something is there in a flow field, there is no message passed. Earlier the message was passed from the disturbance, from the speed of sound, but here speed of sound is less than speed of flow field, so directly this flow field will go and it will hit to the object, it will go and hit to the object like this, okay, it will go and hit to the object, okay, it will go and hit to the object. Once it will hit, then it will recognize, oh, object is here, okay, then the molecules what it is hitting on the object, it will go hit and it will rebound, it will rebound like this, it will rebound like this, okay, it will go and hit to the object and it will rebound like this, okay, it will rebound here, then again it is rebounding here, okay, this part is what, rebounding, this is the rebounding of particles, I must write rebounding of particles, okay, fine. So this particle will go blindly and it will hit to the object, because the speed of flow field is what, higher than the speed of sound, so there is no messenger, there is no disturbance created, directly it will go and hit, and once it will hit and then it will recognize, oh, something is there, so it will rebound, and it is, if once it is rebounding in this direction, so the flow field is what, coming in this direction, so what will happen, there is one thin region will be created like this, thin region will be created like this. In this side there is the rebound particles, this is the rebound particles, okay, and here this side the coming particles are there, and they are colliding to each other, they are colliding to each other, so once they will collide, so there one thin region will be created. I will redraw again. Right, just say this is the very thin region here, okay, this is very thin region created, okay, this side particles are rebounding, after hitting to the object the particles are rebounding, these are the rebound particles, okay, and this side the particles are coming, that is the flow field particles, flow field particles, and all are colliding to each other at this region. So what this region we have, okay, this thin region what it is created here, this is because of the collision of the particles, understood, and this is called shock. What it is called, this is called shock. So if it is normal to the flow field, if shock is formed normal to the flow field, it will be called as a normal shock. If it is formed with different angle, then it is called oblique shock. So these are the rebounding particles, okay, rebounding particles, and these are the coming particles, okay, and this is the colliding zone, no? The particles are colliding here in the shock, this shock which is nothing but 10 power minus 5 centimeter, okay, thickness is 10 power minus centimeter. So there is one region created, and in this region drastic variation of the thermodynamics property like pressure, temperature, density, everything will be changed. So this is the case when this is the supersonic. For that reason, now you can answer it. If somebody will ask why shock will form in supersonic flow, why shock will not form in subsonic flow, now you can answer it, because subsonic flow they have eyes. What they have? Particles have eyes, but these are the blind particles. They don't have eyes. Blind particles. So blindly it will go and hit to the object, and then it will recognize, oh, in this way there is some disturb. I mean, one object is there or some disturbance is there. But how they will know? They will go first and hit, then they will know. But in case of subsonic, they have eyes in the sense the disturbance, which is the speed of sound. First, they will go and hit to the object, and immediately they will pass to the pass message to the behind particles, and behind particles are the flow field, and they will transfer the message. Something is there ahead, and please change your direction. So they will, without colliding, they will change the direction. So the flow field will be like this. So now if I will show the object, so this is the subsonic, okay, this is the subsonic flow, this is the subsonic flow will be like this is what subsonic. They will change the direction, okay, they will change the direction, okay. But in this is the subsonic, but in the case of supersonic, they will not able to recognize. They will go, the particles, they will come, and they will go and directly hit to the object. These are the blind particles, okay. And then once they will go and hit to the object, then what they will do, they will rebound, because this is the solid surface, the particle will rebound like this, okay. And the coming particles will again collide with the rebounding particles. Then very thin region will be formed, and this thin region is called thin region, which is order of 10 to power minus 5 centimeter, very thin, and this thin region called top. And this is nothing but m greater than. So for that reason, in case of supersonic flow, shock will be recognized. In subsonic flow, shock will not be recognized. That subsonic flow, they flows particles, they have eyes, they can recognize the object, okay, ahead there is a object, so they will change the direction. But in case of the supersonic flow, the objects, the particles don't have eyes, you can say in rough word, and they will not recognize something is there, and they will go and hit and rebound. Then that rebounding and collision of the particles will create one thin region, that thin region itself called a shock. And it is thermal conduction will be there inside this thin region. Thermal conduction will be there, okay. It is irreversible process. For that reason, across the normal shock, because of the irreversibility, entropy will rise, and because of this irreversibility, all the isentropic relation like T naught by T is equal to 1 plus gamma minus 1 by 2 m square. This type of formula, P naught by P is equal to 1 plus gamma minus 1 by 2 m square whole power gamma upon gamma minus 1. All the formula isentropic relation will not work across the shock. It can work ahead to the shock, it can work behind to the shock, but across the shock, not a single isentropic relation will be used. Why? Because it will be failed. Alright, that is the one conclusion I must say about the shock. Already it is explained in this diagram also. I think it is now clear about the formation of shock. So this is what normal shock. Now because the object is what placed, this object is what placed, object is what placed, object is placed normal to the flow, okay, here. So if the two types of object you can have, like this is the object which is normal to the flow field, okay, and this is the another type of the object, this is the another type of object which is not exactly normal to the flow field, okay. So if the object which is normal to the flow field, so this is the case of normal shock. Okay, and this is the normal shock condition, because the object is what you know here going to hit normally, so whatever the shock will be formed, it will be normal shock. But this is the object which is the like uh, with some inclination with the flow field, so it will have a oblique, or oblique in the sense any inclination is there. Okay, so here, because of the same pattern, you may have this is the oblique shock now, and here you may have normal shock. This will be the normal shock. But I'm showing you like how the shock will be formed, but it doesn't mean that flow will not pass. Okay, if you study the normal shock analysis and do analysis and all, if you do, then this will be the normal shock. Okay, you have to show this is the normal shock in a flow field, and the flow you have to show like this, and again this side also flow you may get. This is the analysis of the normal shock. Okay, so similarly here also, otherwise you may think, okay, if the object will come inside the flow field, then how that flow will go ahead, it will stop. Practically it is correct, but like to like analyze the normal shock, we can say this is the object and flow will rebound and all. But if you go for that calculation, so you show this normal shock here, and this object obviously will not show there, and then you can check the properties variation. Suppose here pressure is P1, here temperature is T1, density is rho1, Mach number is M1, and after the shock pressure will be P2. This is the analysis. Okay, density will be rho2, Mach number will be M2. So similarly here also, because this is the oblique shock. Okay, so after the formation of oblique shock, that flow will also turn. Okay, and how it will turn and why it will turn, that is the secondary analysis. Once I will show the mathematical model for the oblique shock, so I will tell you. So this is what oblique. Okay, this is the oblique shock. This is the oblique shock, and this is the normal shock. This is the normal shock. Okay, so basically here you understood the formation of shock first of all, because that is very important. Formation of shock is very important. Okay, once you understood the formation of shock, then we can go for the and you know the what are the application of shock wave. So basically that shock wave you can understand in this way, like in medical, the use of this normal shock we had seen. What is that, like if you go for the application of shock wave, it is noted in the medical, in urology and orthopedic. Okay, it is able to distinguish kidney stones and to cure. Okay, and certain soft issues, tissues disorders. So because that is the part like bones and all. Okay, the stones and all in kidneys. So if you pass the shock, then if the pass the flow, and if shock will be formed, it means something is there, the object is what there, yes or no. So for that reason, the application of shock wave is what noted in medical very in very significant manner. Okay, like in urology and orthopedic, these are the departments they are using to identify the kidney stones and all. That is the use of shock wave in medical, and obviously in engineering many places, like once aircraft, supersonic aircraft is what flying, or CD nozzle analysis, rocket engine, if you see that is space shuttle CD nozzle, that Mach is what all 10 Mach, 15 Mach. So obviously hypersonic flow will be there. So there is also the actual formation of the shock, and because of that pressure, temperature, density variation. So that that is very significant application in the engineering, but I'm saying that shock analysis, it is also used in medical also, just like urology and orthopedic I told you, or to identify the kidney stones and all, there also the shock wave they can use. All right, now so this part is all done. Now we'll go for the equation. What equation will be used in case of the, if we'll say normal shock wave, then what type of equation will be used? That is the one very all three equation, like energy equation and momentum equation and continuity equation for the shock, that equation will have a different manner to write. Okay, like earlier what we had seen, it was uh, what we had seen already, it was maybe for compressible, maybe for incompressible we had seen, but separately for the normal shock, again the conservation equation will see, and that equation only will be used across the normal shock. Okay, previous equation what you had seen, momentum equation and all, that will not work here. So we'll see that it's very simple only. So I will write here the, see, so first I will start normal shock. Normal shock. After this normal shock, we'll go for the oblique shock. First we'll see the normal shock. Okay, so normal shock, first of all you need to remember, this is the 1D, one dimensional flow. Okay, this is also very important, one dimensional flow. I can say, suppose there is the flow field, so this is the shock formation in a flow field. This is very thin region, but I zoomed out and I'm showing this is the normal shock. Okay, and I can take the region. Okay, it's a very simple one. I can take the region like this. As I told you earlier also, that isentropic relation will not work. Why? Because it is the irreversible phenomena, and entropy will rise here. Okay, so I can say this is the upcoming flow. Okay, upstream and downstream, and this is what, downstream, across the shock. So upstream, you can say that this is the upstream. Okay, let me write. This is the upstream and this is the downstream. Okay, and this is the rectangular control volume I have taken. This is the rectangular control volume, and inside that this is the formation of shock. Okay, this region called 1 and this region called 2. So I can say here, the in this region pressure is what, P1, temperature is what, P1, density is what, rho 1. Okay, and velocity is what, V1, Mach number is what, M1. And in downstream the pressure becomes P2, temperature becomes T2. Okay, density becomes rho 2, velocity becomes V2, and Mach number becomes M2. Always remember, this M1 must be greater than 1, then only supersonic will be there, and after shock formation this M2 will be subsonic, means it will be less than 1. Okay, so here it is supersonic, that is okay, but once shock will be formed, that flow will becomes subsonic. That you will understand by once we'll do the derivation. Okay, so here no need to write all the statement, what is the P1, P1 rho 1. You can say upstream means whatever the flow coming towards the shock, and now you assume that shock is formed already. Okay, so whatever the flow coming towards the shock called upstream flow, and whatever the flow going away from the shock called downstream. So upstream flow properties are P1, T1, rho 1, V1, M1, and downstream flow properties are P2, T2, rho 2, V2, M2. If you want to write entropy also, S1, S2, you can write, no? S1, S2. S1 is the entropy here, and S2 is the entropy here also. That you also you remember. Okay, so I'm going to write the continuity equation here. In very short, I will write two lines only for the equation. This is the continuity equation, because all the conservation equation I have explained in integration form. So that same integration form I'm going to use. What is the integration equation? Continuity equation I will write in integral form. So it is nothing but dou by dou t triple integration of density into volume. This equation I have written. This is the integral form of the continuity equation rho v ds. This is the continuity equation. Okay. So for steady flow, dou by dou t, this term, okay, will be 0. So what equation we will have? Check. We will have double integration of rho v into ds equal to 0. ds is the area. Okay. So here you can say, because both are velocity v1 and v2 we have, okay, ds is the area, so area will be same both side, okay, like if this is the shock here, this is the shock here, so whatever this is the shock now, okay, so for this shock whatever the area, both side upstream and downstream it will be same, and whatever the velocity it is nothing but this side v1, and what is the velocity here, it is nothing but v2, and what is the density here, rho 1, what is the density here, rho 2. So both side area is what, same by magnitude, but direction is what, just opposite, yes or no? What is the direction of the area? It is normal to the surface. So if you check the area of the upstream, so this area will be s1 in this direction, and this will be opposite, this will be in this direction. So along the flow, this will be the positive, and opposite to the flow, so this will be negative. So in the sense, now if you write the equation, you will have a rho 1, v1, s1 is the area, okay, that is for minus 1, okay, and because this area will be along the direction of the flow, so it is rho 1, rho 2, v2 and h2, okay, and here if you check, this is equal to 0, as you know area s1 is equal to s2, that is the area, this area is what, constant, yes or no, both side, so you can say it is nothing but rho 1 v1 is equal to rho 2 v2. This is what continuity equation you need to remember, okay, this is the continuity equation across the normal shock. So this equation will be valid, continuity equation across the normal shock, okay, valid across the normal shock. I must write valid across normal shock. This is what continuity equation. Continuity equation. Similarly, we'll go for the momentum equation. This one is clear, okay. This is the continuity equation and it is valid across normal shock. Now we'll go for the momentum equation, okay. So we'll write momentum equation, okay. In this momentum equation again I will short out and I can say no gravity force, okay, even though no viscous force, so we'll have the, you know, that mass flow rate, influx, outflux, and the pressure force. So you can say momentum, that is the mass into velocity, and uh, pressure force will be there. So I can write here, we are considering no body force, okay, no body force. We are considering no body force and no viscous force. So we just recognize and Remember the previous, recall that momentum equation. So that momentum equation now, if you recall, I have given the integral form. So rho v into ds, and then this is the mass flow rate into velocity component will come. V is equal to, that is the pressure force here, P into ds, and this is in x direction, okay, because we are talking about x direction, because that pressure force will be in y and z direction also. But this is the 1D, because this is what, this is for 1D flow, so only one direction I have to take, so I have taken x direction. If you open it out again, I told you ds area will be along the direction, along the upstream area will be just opposite to the flow, and downstream area will be along the flow. So plus minus here also will come, just like here plus minus I have shown you. See this area s1 I have shown you, rho 1 v1 s1, because area is a vector quantity. So plus minus here I have shown you. So same thing here also, area we have, so this will also work. So I will write that directly this equation. So upstream it will be rho 1, okay, it will be v1 and v1, and here also, because you are talking about the velocity upstream, so this velocity will also be v1, so v1, and here it is nothing but I must say minus of s1, okay, minus of s1 plus rho 2 v2, again v2 will also come, and this is the plus of h2, okay, and here this is nothing but, similarly you have to do, because minus sign is already there, and here also you have to write what, upstream will be p1 minus s1, and downstream it will be p2 and s2, okay. And I told you how that upstream and downstream, that area, see area is always normal to the surface, so you can consider this is the normal shock, this is the normal shock ns, and normal to this normal shock will be the area of the normal shock. So area will be just perpendicular to the surface, so this s1, check this flow direction is in this direction and area is what, just opposite, hence you can say minus, and here area and flow direction is what, same, so theta will be 0, and here theta will be 180. So cos 180 is what, minus, and cos 0 is what, 1. You can understand in that way also, okay. So and similarly for the pressure also you have to do. So this is what, this is nothing but rho 1 v1 square, okay, minus plus rho 2 v2 square, because area is constant both sides, so take s common both side and cancel it, and this is minus minus plus, so it is nothing but p1, okay, and p1, and this minus will go and multiply here, so p1 minus p2, s is cancel out, okay, everywhere s1 is equal to s2. I told you that area will be same both side now, so I can say s1 is equal to s2, which is nothing but constant area. So what you will have, this equation, check. So this equation is nothing but called momentum equation. In very short I am giving, and I am thinking like this much, because if I will explain again this conservation equation, so it will take so much time. So now if you check, segregate this, then what you will have, p1 plus, you will have a p1 plus rho 1 v1 square, okay, is equal to p2, check, this p2 is what, take this side, so p2 plus rho 2 v2 square, p2 plus rho 2 v2 square, this is called momentum equation, okay. This is the momentum equation, this is the momentum equation valid across normal shock, valid across normal shock. This is called momentum equation. Okay, this is very important here. What is P1, P2? Already I have told you, P1, rho 1, V1. V1 is the velocity, don't think this is the volume, V1 is the upstream velocity. V2 is downstream velocity. Already I have given, but again I am writing so that there should not be. Similarly, P1, rho 1 is the pressure and density for upstream, P2 and rho 2 will be pressure and density for downstream. So this is the momentum equation which is valid across normal shock. Okay, remember this. Similarly, you can write energy equation. So energy equation, I will not go for derivation. I will write. Okay, this is the energy equation. 1D, 1D energy equation. So this is the similar we had seen for compressible, because shock is also a compressible flow. It's not incompressible, it's a compressible. So for compressible, I had given energy equation. So H1 plus V1 square by 2 is equal to H2 plus V2 square by 2. Or what you can write, H1 also you can write C1 CPT1 plus V1 square by 2 is equal to CPT2 plus V2 square by 2. Okay. So this is the energy equation which is valid across normal shock. Need to remember. So